better things, like how much money you might make when you graduate. So this last section we're going to cover, it's called testing robustness and pitfalls. So the key detail in this beginning portion here is logic verification accounts for greater than 50% of design effort for many chips, meaning everything that we've done up to this point is about half of what happens in industry. Beyond that, there's people who it's their entire jobs to test chips, to make sure they work, to come up with all these different ways of ensuring that they meet everything. And here, there's a very famous bug. It's the floating point division bug. Intel did not properly check to make sure that they had their overflow on their floating division portion of their data path. So as a result, occasionally, I mean, it wouldn't happen very often, but it resulted in logic errors. And you can't have logic errors when you're doing calculations, especially memory, doing all these different things. So they didn't realize it until they'd shipped out over 1 million of them. And the recall effort cost them $450 million, which in 1994 money is about $1 billion now. So that's quite an expensive. So now Intel spends a ton of money investing in test engineers. And so I have the Glassdoor. So test engineers typically make about $100,000 to starting. So that's the reason why I want to include this particular section, is because if for some reason, you kind of want to get a good idea into how to do a test engineer, you can put that on your resume and you can pursue this kind of a job and they compensate you well for it.
Is that what a bachelor's is only?
Yeah, this is, well, typically, it's either they have a range here. So the base salary is the kind of the average, and they have like 223. If you're going out to California, you want to make sure you get a decently paying job because of their high taxes. So I would not if you're like getting $60,000, $70,000, you'll be living in a closet pretty much. It's not that good. But if you're getting 100,000 and then you're starting to get all kinds of stock bonuses, profit sharing, cash bonuses, and you negotiate it well. And by the way, if you ever need help with a company negotiations, I'll be happy to do it. So anyway, just a reminder, like, when are you going to learn this? Well, they might pay you very well when you learn this. So, and so for the grad assignment, this is the detailed version of what happened with the floating division unit. So as you all know at this point, and I'm sure you all could agree to this, one of the most time-consuming aspects of CMOS design is in troubleshooting problems.
Well, just also coding too.
Coding, troubleshooting, all that stuff, right? So when I was in the nuclear Navy, they had this 5-step process for troubleshooting. And this is a good way to kind of get your mentality around how do I figure out a problem and how do I solve it. And what I'm going to do is I'm going to describe you this 5-step method, and then we're going to go through some basic troubleshooting techniques to kind of get you the idea of how this can be applied. So this may seem like common sense, but oftentimes it's not. Identify the problem, recognizing that a problem exists and observing its symptoms. So the trouble with electric VLSIs, it gives out sometimes the compiler errors or the issues that come up don't seem to make much sense. They don't really, it doesn't always properly describe how to troubleshoot the problem. So being able to identify what it is really helps. Take preventative action. So what this means, particularly in a Navy context, is if you have a board where it has some sort of fault and it's not working, you switch out and you have a backup board. So if y'all have ever seen the movie Crimson Tide and they have a board fault go out and it costs 2 hours while they're all fighting and Denzel Washington and Gene Hackman are deciding whether to nuke Russia. That movie would have actually lasted 30 seconds because they would have just put in a new board. So a short-term action that's meant to put a circuit in a safe condition while work is performed to correct the problem. Determine the cause of the problem. So this is where the process of elimination, separating those factors that are not causing the problem from those that might be causing the problem. And we're going to be going over this half splitting method, where we're going to be splitting up the circuit in half and determining whether or not it's proper, it's working at certain points, and allows you to narrow down the focus of where the error is. Step 4 also seems intuitive, but it can be hard. Correct the problem, making adjustments and repairing or replacing equipment. And so where is this issue? When you've done coding, you know that you've got 99 bugs in the code. Take one down, pass it around, 128 bugs in the code. You want to make sure that your fix actually helps instead of hurts, And then you have to return the circuit to normal operation. So here's the simple example. So we have a full adder, and we have some outputs. So we have a sum output, which appears to be correct, and a carry output where we're getting some indiscriminate values here, right? So we have two undefined outputs, 0, 1, 1, and 1, 0, 1. So we have identified the problem that we have incorrect outputs on the carry out, and that our sum value is correct. So in this case, if you were taking preventative action, you would remove the board from the computer using appropriate safety procedures. And then step 3, you're going to determine the cause of the problem. So if you know sum is correct, you can do this half splitting method as I've done here. And you can make an educated guess that if all of this is working properly and giving us the right values, odds are good that we're actually going to get the errors over here. In this case, we simulate these input wires, and then we test these values for P and Q. Okay, so we've got it split up, and then we half split again. So we test P and Q, and then we look at the results of the OR gate. So you have these values here. So what's going to end up happening is that the AND gates are correctly, so we know that something's going wrong in our OR gate. And so what you don't know underneath, and you can provide this, is that if you design the circuit like this, you'll actually get these specific outputs when it's actually 1, 0, right? So when P is 1 and Q is 0, you're going to get indiscriminate values because it's not going to actually be able to create the inversion regions to put an output there. So in this specific case, you correct the problem by fixing the OR gate. You add the second NMOS transistor. You still have the inverter as always, and then it puts the output in the right spot. And then return the circuit back to normal operation. So troubleshooting tips and advice. Regularly back up your code and work. Never presume or assume anything. Always try to recreate the problem unless there's a personal safety concern. Writing all test steps and data. So this is something that I do a lot when I'm working on projects. If I get to a specific point, and those of you who had me in 385, I would come up with these detailed circuit diagrams and try to figure out everything in terms of timing and lay it out before I wrote a line of code. You want to do the same thing when you're troubleshooting. You want to okay, this is where we're at. This is what we need to do. Break it down. Try to come up with the steps that you need to do and document everything. So that way, if you make some sort of mistake while fixing it and it gets worse, you can backtrack your steps. And then also, if you type them up and you are in lab 3 and you're struggling, you can copy and paste them and put them into your challenges section. So that's a pretty definitive way to prove to me that you at least understand what's going on and that you've done the work. And then never rule out having more than one problem. So then I actually told this joke, and here's Grumpy Cat. Grumpy Cat's like all of us. We don't like dealing with the project sometimes. So look for common components. Okay, so this part, if you synthesize cells, so you go through your whole process, you design the polygons, you've designed a specific full adder cell, and then you see a recurring problem, it's entirely possible that instead of having to go through and fix every full adder, if you flatten it out. I've seen people do this. They'll flatten it out and they get the same error, and they like, why are there 35 of these errors? Well, it's because you have the same error 35 times. So if you go back to the cell, fix it there, instead of having to pull your hair out, you do one smaller error. The next example problem is a good example of what happens if you don't consider this piece of advice. So, okay, so we have the following full adder in this truth table here. So each of these nodes that I've identified describes what happens when we get a specific input, right? And so what's going to happen here is that we realize sum and carry out are both wrong. So we're going to do our half splitting method. So this is a good half split point. I think we've done here. Testing 3, 5, and 6, we find that 3, 5, and 6 have correct values, right? So this values were correct, this value is correct, and this value is correct. But that 4 is wrong. One has this, one has the same values as 4. So testing for set values 7 and 8, we see that 3 and 4 are properly calculated based on those specific inputs. So we get wrong inputs on 4, but based on those wrong inputs, we're getting 7 and 8 correct. Therefore, there are no errors in this half of the circuit. So we know that the error is up here, right? That makes sense so far? Next, we split the circuit at node 1, here. We test A and B. The A inputs and B inputs are correct. Then we test 1. So we have, what's going to happen is if we look at the truth table, we're going to see that A and B just happens to match A, right? So node 1 here matches the A input. So what we're discovering is we're having some sort of B is going to ground or something like that. That means that we specifically see the, okay, so we test A and B, therefore give A and B. So now what a lot of people would do is they say, okay, well, I'm going to fix this and then move on. But if you did fix that, if you fix this specific XOR gate, what's going to end up happening is you're still going to get wrong values on the sum output. You're still going to get wrong values, and then people go, they have to put it back in, and they fix everything, and this takes hours and hours and hours. This step here will save you tons and tons of time. So what you want to do is you do the half splitting, but then you have to test this part too. Right? So we text the XOR to the right, we see that input 2 is correct, but sum is wrong. So I'm observing output sum, we notice that sum from the XOR gate matches input 1. So if we actually go to input 1, here, and go to sum, they match. And we see that A matches 1 and matches sum. So what's actually happening with this full adder is the A input is going through here, and the XOR is not caring about what's going on either of these other inputs. So it turns out is we have the same error going on in both XOR gates. Does that make sense? So what's going to happen is this at the cell design level, we have something what's known as a stuck at 0 fault, meaning that no matter what is being done, that particular wire is stuck at ground. A stuck at 1 fault is when it's tied to VDD, and no matter what you do, it stays in VDD range. So finding these is a big testing problem. And so that's why I try to avoid this simulate and tweak approach. So if you find a stuck at for input B, you'd get the following, right? So if you just fix that XOR gate, you're still gonna get wrong values. And so people would try to go back and try to figure things out. It would take them a long time. So I'm presenting that in an attempt to save you all time. Okay, so there are 3 types of testing for CMOS ICs. The 3 types are formal verification, silicon debug, and manufacturing testing. So formal verification, which is what we're going to spend the majority of this section doing, tests that confirm the chip performs its intended function. Pretty straightforward. Silicon debug, tests that confirm the fabricated chips meet design and performance metrics. We kind of covered this in some detail last section where we're talking about PVT tests and how do you make sure the seal rings are taken care of and that all the there's no defects that could potentially cause faults or overheating or inadvertent power consumption. So silicon debug goes into that. And then the last part is the manufacturing tests. So the tests are concerned on each manufactured chip before shipping to the customer to verify that silicon is completely intact. So for the first part, the formal verification, does the chip simulate correctly? So it's usually done at the HDL level. Verification engineers write a test bench for HDL. Now here's the key part, and this is where we're going to be spending on. You can't test for all cases. If you're testing a full adder, right, or a floating point, even more so, a floating point divider like Intel had to deal with. You know, if you're dealing with a floating point, you have two 64-bit inputs. So that's 2 to the 64 times 2 to the 64 possible test cases. And the thing that they missed happened only, you know, it was only like 5 or 6 cases. So you think you'd come up with a comprehensive test. You know, do brute forcing it is, you know, difficult. So looking for corner cases, things that come up all of the time, things that typically will define the rest of the circuit. And then you trying to break the logic design. So here I'm talking about you want to test a few random inputs here. Good tests require ingenuity, so that's where we're going to get into. Logic bugs versus electrical failures. This, I mean, I could go into tons of detail, but common sense says that logic errors mean that you have designed the circuit wrong logically. Electrical errors mean you've designed the circuit correctly logically, but there's some sort of electrical physical error, stuck at 0 fault, stuck at 1 fault. You have not properly sized your circuit so they're not getting to the noise margins. You've put your voltage domains in the wrong order, something like that, that actually is creating issues in your circuit. And the design rule checks are supposed to catch a majority of these. And then manufacturing tests is a speck of dust on a wafer is sufficient to kill the entire chip. So you want to make sure that everything's clean. That's why you do have all these clean rooms. Yield of any chip is 100%. And then typical defects, I mean, layer to layer, shorts, you know, we remember talking about metal 1, metal 2, and then when you get to these smaller and smaller transistor sizes, you have to have more and more metal layers. So if you short between metal layers, you're going to cause a lot of problems. Discontinuous wires, missing or damaged vias, shorts through the thin gate oxide, and you know, a lot of these are, okay, so here's some good pictures that describe it. So metal 1 shelving, you know, you're trying to see it doesn't quite connect. So here's a bridge. You don't want these are supposed to be logically different, and somehow this has caused a short. Open defect, you can see how it's not actually connected. Metal 5, and obviously this is wrong. Spot defects, what happens when you have impurities. And then you're missing an open contact there. So functional equivalence works at various levels of abstraction. Actually, that covers the whole thing. So behavioral specification, how should it behave? That's where you get your formal verification that we discussed earlier. So you come up with some test vectors to be able to try to make that work. If it doesn't work, obviously you need to go back and start again. Then the register transfer level specifications, you need to worry about timing analysis and noise. Does it reach the noise margins? Do you have a sufficient power? Is your electrical effort properly accounted for? Structural specification, that's where you get your layout versus schematic. Power analysis, design and error rule checking, and parasitic extractions. Is your parasitic delay properly accounted for? And then physical specification, of course, is it actually meeting the specific, for 22 nanometer, 45 nanometer, your design case. So combining chips, how do you test chips that return from foundry? So what's going to happen here is the short version is you can actually use what you learned in 385 on embedded boards to run these test vectors. So you can combine what you learned in this class with 385 and be able to do it. So you can power the IC to vary supply voltage and measure power dissipation. So you can actually construct a circuit board that provides the following attributes, and you can use a Verilog or VHDL test bench, clock inputs as required, make sure that it meets the timing constraints that you have, real world signal connections, so being able to put a lot of different things, potential power signals that the chip might actually encounter when it's used in the real world. And then a digital interface to a PC, whether it's a serial or parallel port. So you can test your synthesized chip. So you see how the chip is in the socket here, right? This is our CMOS. So we put into the board, and then we have our I/O and variable power supplies for our different VDDs and everything like that. So you can do custom signals. You have analog I/O, PC serial I/O, logic analyzer. This is where you can actually analyze the output logic to make sure that you're actually passing you're doing your formal verification properly. So there's a couple of basic issues that may come up. If a chip simulates at the gate level, then it'll probably do so when it actually does it in silicon, especially if it passes timing. But if it's slower than predicted, you just fix the slow clock rate or raise the supply voltage to provide more power. If the circuit has a race condition, meaning that we haven't properly buffered our circuit, we actually have to fix the circuit. Remember, the circuit may be fixed by changing the logic, not with the clock. Dynamic logic problems, meaning we've tried doing these circuit families and we've not properly calculated those out. And then crosstalk problems, you got to fix the wires and wrong functionality, you have to redesign the whole circuit. Okay, so 9.2, this example here, consider testing the MIPS processor. So the MIPS processor, now we all know, either it's 8-bit or 32-bit, depending on what you're implementing. Explain the difference between the test you would use for logic verification or silicon debug and the test you'd use for manufacturing. So since you all know that an exam is coming soon, this is a good type of interview type question. So logic verification should test that each operation can be performed. So you have R-type and I-type and J-type instructions. So logic verification will not necessarily prove that an instruction works for all possible addresses and data values. So can you take a few test cases and run R-type instructions and I-type instructions? Does it branch with specific test cases, certain corner cases? In contrast, manufacturing tests must prove that every gate operates correctly. They ideally simulate each gate to produce both a 0 and 1 to ensure the gate has not been damaged. So you got to try to find these stuck at 0 faults. The manufacturing tests may be the only test applied to a microprocessor prior to being placed in the system and used. So basically, what we're saying here is that logic verification, if you're the larger your circuit gets, especially when you're working with billions of transistors, can become prohibitively difficult to try to brute force it. Even coming up with corner cases gets a certain amount. So the formal verification and the physical testing is what you need to do. You need to make sure, go down to every gate level and say, all right, I have an AND gate here. I have a 1, 1 on the input, a 1 needs to come out. I have a 0, 1 on the input, the 0 needs to come out. A 1, 0, a 0 needs to come out. So I need to come up with the minimum number of cases to actually figure that out for a gate, right? So the reason why I didn't say 0, 0 is because I've already tested that a 0 on both inputs will produce a 0 on the output. And we'll discuss that in more detail later. So coming up with the most efficient ways of doing that becomes very important. So, and then the thing that you need to do is something called ATPG, automatic test pattern generation. It's a process to determine an input sequence that distinguishes between the correct circuit behavior and the faulty circuit behavior caused by defects. And so we're going to call this observability and controllability, reduces the number of test vectors required for manufacturing testing. So I just described what's known as controllability. Can you actually control the output based on the input? And so 9.5, a stuck at fault assumes that all failures cause nodes to stay at 0 or 1, shortened to ground or VDD. And so when I say a single stuck at fault, there are more complicated algorithms where you might have more than one. I personally believe that the D algorithm we're going to be covering in this section gives you a really good understanding for what you need to be able to do in industry and dealing with multiple stuck at faults, which actually rarely happens. If you have multiple stuck at faults, the issue is not with you need to go test the circuit. There's something fundamentally wrong with your foundry. And so to activate the fault, this is what I was saying. So you have an AND gate, and let's say the AND gate has a stuck at 0 fault, right? So you're not going to find it if you do 0, 0, 0, 1, or 1, 0, right? Because you're going to get the output that you expect. So if you're suspecting a stuck at 0 fault, the one thing you need to do is 1, 1, because that's going to put a 1 on the, it should put a 1 on the output, but a 0 actually comes through. So that is what we define as observability. The ease of observing a node by watching internal output pins. So that process I did was just 9.6. 9.7 is controllability, which is putting the inputs here. The ease of forcing a node to a 0 or 1 by driving the input pins of the chip. So activate and propagate. When we go through the D algorithm, you're going to see that those are the main stages of the algorithm. Activate, propagate, and then repeatability of a system is the ability to produce the same outputs given the same inputs. So that's where you get your faults that are intermittent, which are always fun. Sometimes you have some sort of example, we had that if you have a connection that is poorly made, sometimes it'll actually work and sometimes it won't, and you'll go, why isn't I'm getting the right answer sometimes, I'm getting the wrong answer sometimes, and I can't figure this out. That's where repeatability comes into play. And so this other thing, we're going to be coming up with input vectors. So fault coverage, percentage of a chip's internal nodes checked by a set of input vectors. So if you have an 8-bit adder, right? And so you're adding, I'll just call it a 4-bit adder, right? So you're adding 0 and 1. So if you're just adding 0 and 0, you're not going to be able to find much of anything. So that's what only cover 25%. So you're going to try to come up with some type of adder that comes up with a vector like this, where the right answer gives you all 1s. So, but if you're getting a 0 somewhere, you can narrow down where the fault is. Does that make sense? So that's where fault coverage comes into play. Then composite logic values are used to keep track of the error propagation, considering values in both the fault-free circuit and the faulty circuit. So these are the fault-free circuit N is our theoretical correct circuit that we've tried to design, right? And then NF is what we actually have. So NF is the reality circuit. And so we're going to have these values D and D bar. So what this means is when we have vector output and output fault, this means if we are expecting a 1 and we're getting a 0, and then, or if we're expecting a 0 and we're getting a 1, when we denote these on the circuit, that's going to be D and then D bar. When we have the correct values, they're just denoted by 0 or 1. And so we're actually going to be going over what happens when you have a 0 and D, right? If you're ANDing those, no matter what you have on D, if you're doing a 0, you're going to get a 0 on the output if you're ANDing it. If you have a 1, if you have an OR gate, if you have an OR gate and you have a D on the input, then it's dependent, if it's 0, you're going to get D. And if it's 1, well, you're always going to get 1. So that's where the challenges come into play. Okay. So if you have D and D bar and an input, Well, they're going to be the opposite no matter what, because it's 1, it's supposed to be 1, and supposed to be 0 as the two inputs. What we're getting is 0 and 1. So the output of an AND gate would always be 0 here. And so sometimes what happens is you get a single stuck-at fault, which propagates because due to fan out, which then you get things like this. And so these are all the truth tables. So V and VF is 0, 0, 1, 1, 1, 0 is D, and 0, 1 is D bar. So when you AND them, this is your conventional truth table. So if you're ANDing D and D, you're going to get D, right? If it's 1, 0, and 1, 0, well then if you get both 1s, you're supposed to get a 1 on the output, right? And if you AND both 0s, you're supposed to get a 0 on the output. So you're going to get D anyway. So here, D and 0 is ANDed. Everything with 1 here is ANDed. D bar, of course, is D bar, and then X is don't care. Same there, D bar and D bar. When you AND those, you're getting 0 and 1, 0 and 1, right? Is this starting to make sense? Okay, good. And then like we proved earlier, both the times you AND D and D bar, you're going to get 0. You get a 1, obviously you put in a 1 no matter what, you'll get a 1 on one of the inputs. And this is your conventional OR truth table. So if you get 0, you'll get a D on here, right? So you get 0 on the input of the OR, whatever D is going to go out. And then D, this portion right here, when you're ANDing D and D bar. So if you do D and D, right? D or D, so if it's 1 or 0, 1 or 0, you get to the OR. Well, if it's 1 and 1, you're going to get a 1 on the output. If it's 0 and 0, you're going to get 0 on the output, so you get D. Same thing with D bar, it's just flipped. This other case, what's going to happen is if you get 1 and 0 and 0 and 1 for D and D bar on the input of the OR gate, well, 1 and 0 is 1, and 0 and 1 is 1. So that's why you need to understand that truth table. And then last but certainly not least, XOR. Most of the time you're going to get a D bar here, right? Just because D and 1, XOR 1, sorry, that's XOR 1, right? If it's 1, it's going to come out to 0, and if it's 0, it's going to come out to 1. And so the controlling input we have here, so if it's a 0 on any one input, you're going to get a 0 on the output. And then NAND, you're going to get a 0 on any input, you'll get a 1 on the output. Does that make sense? For OR, you go to 1, you get a 1. For NOR, you get a 1, you get a 0. So that's where these controlling values, so you have that observability and controllability. So knowing those values will help you out quite a bit. So now we're going to talk about using the full adder circuit from example 9.1, and now we are adding a stuck at 0 fault at the second input. Show the composite logic values for input value combination 1, 1, 0. So here we have had a 1, 1, 0, right? So this is the equivalent of just 1 and 0. So what's going to end up happening is this should be XOR, so this should be 1, and we should be getting a 0 on the output. But we have a stuck at 0 fault, meaning this one is always 0, right? So what's going to happen is we should be getting 0, but we get 1. So this is technically D bar, right? So that means we get D bar in here, and then this is going to be 0. So D bar XOR 0 is going to be D bar again, right? And so our error propagates here. So we have D bar and 0, which means we're going to get 0 here. Also, since this is stuck at 0, that means we're going to get a 0 here. Right? Oh no, it's stuck at 0 at the input of the XOR gate. Sorry. Stuck at 0 at the input of the XOR gate, which means we're getting the correct value from B here. Does that make sense? So I should make, I'm sorry, what's that?
How do you know when you have, so you have like a 1, 1, but then you just have a 1 at the bottom circuit?
Oh no, okay, yeah. So basically what I'm doing here, yeah, no, that's why I have them both there, because I want to explain it. So here, what this correlates to is, in this case, 1, 1 means that it's supposed to be 1 and it's actually 1, right? So then in the notation, to save you time, how it's done in testing, that's just defined as a 1 here. So what this circuit is I've gone through what it should be, what it actually is, what it should be, what it actually is, and I've translated that into this, right? So this is the correct answer. So when you write it up or on an exam, that's sufficient for full credit. So what this means is this was 1 and 1, this was 1 and 1, and then we got a 1 here and a 1 here, right? So what's going to happen is, since it's stuck at 0 here, what we should be getting is a 0, right? And then, but because it's 1 XOR 0, we're actually getting a 1, which in our notation for testing is D bar. And again, we get a 0 here, so we're supposed to get a 0 here and a 1. XOR 0, we should be getting a 0. What we're actually doing is 0 XOR 1, which again is the notation for D bar. Does that make sense? All right, good.
You had it correct on the output, it would just be
Yeah, okay, so if,
so 1 over 1 would be.
you mean on the output, you mean if it was just like,
Yeah.
if it was just here, we'd have stuck at 0 fault?
Right.
If it's stuck at 0 fault, what ended up happening is this would just be 0 no matter what. So what would happen is, let's say we had, so your question is, we no longer have this stuck at 0 fault at the beginning of the XOR gate, we just have it here at some, correct?
Right.
So what's going to end up happening is, it's, what we should, so it should be 1 and 1, it should be 0, right? It should be 0 and 0, it should be 0 in this test case. So what's going to happen is this particular, this is a great question. This particular input vector did not find the fault. So what would have happened is if we had a 0 on B, then what happens when we get 1 here, and 1 and 0 XOR should be 1, but we're getting a 0, so that input vector does detect the fault. Yes. The D represents propagation of error. All right. So this is kind of, this is going to look like a complicated algorithm, but when we go through the example, it will make sense. So you have to set all values to X. We call this justify. So what's going to happen is we have a L stuck at V fault. So what the L is the specific node. And what we're going to do is we're trying to find a stuck at 0 fault. And then we actually input to this justify portion of the algorithm the inversion. So if we're trying to find a generated test for a stuck at 0 fault, we put 1 into there. If V is 0, then we're going to try to propagate D through, so we'd propagate 1, 0. Or otherwise we'd propagate D bar, 0, 1. And then we're going to return all the values. So what we're going to try to do is we're going to try to find the test vectors required to cover specific faults. So justify, so here we actually got the negation, but that's what's put into this portion of the algorithm. We set that specific node to that value. So if we're testing for 1, we put in 0, and then we set that node to 0. If that is a primary input, then we return. So what happens is C is going to be the controlling value of this node. So if we have an AND gate, the controlling value is 1. So we're going to do an inversion of L. So whatever L is, so if we had 0, right, the inversion becomes 1. So this invalidate bit becomes 1 XOR 1. So if invalidate is equal to the negation of C, that means we're going to keep going through and justifying again. And when I go through the steps of the algorithm, this is going to make a lot more sense. And then justifying one input of J, if they are not equal, I mean, if in this case if they're equal, then we're only taking one value. So basically what this means is that, let's say we have the controlling value, and we determine that the controlling value is not true. We've inverting it. So in this case, let's say we have an AND gate, a 3-input AND gate, right? And we're trying to figure out if this invalidate value is actually a controlling value. So if I put a 1 here on one of these inputs, I'm going to get a 1 out no matter what, which is why we're doing select one input, because if it's a controlling value, we do that. If it's a 0, that means I have to test all the rest of the inputs until I find a controlling value in order to propagate the result. That's why we're doing each one here. And so the last stage is going to be propagate. So we have this error value, so we've called that here. So we're actually trying to propagate the error through. We're setting the node to the error value. If the error is the primary output, then we're just going to return. So that primary output means we've actually reached the end of the circuit. And so we then take these three values, K, C, and L, right? And then we're actually going to propagate through using our algorithm. So for each input of J, K that's other than L, so that's not the specific node that we're picking, we're going to be going through and justifying the opposite of the controlling values. And so you're like, okay, that's great. You've thrown a bunch of gibberish at me. Can you show me an example that makes that simple? Here we go. Okay, so we have this stuck at fault 0. So we are trying to find a input test vector that determines that we will definitely find a stuck at 0 fault at node F. Correct? So that's what we're doing. So here's how what we're doing relates to the algorithm. So first, we have to generate, main test generate, we're generating a test for stuck at fault 0, right? That's the initial algorithm. So what we do is we invert, we justify F at 1. That means, according to our algorithm, I is going to be equal to 0, C is going to be equal to 0, and invalidate is going to be equal to 1. So we justify A as 1, and B is 1. This means that in order to, we pick the opposite value, and we're trying to figure out how to actually get it such that if we produce this specific vector, we're supposed to get 1, but we get 0 instead. So the reason why, in this case, what's happening here, this portion of the algorithm was where I talked about you have to go through each input and use this invalid bit. The reason why is because here, this solution, so A is going to be 1 and B is going to be 1, because if we only did, let's say this was a stuck at 1 fault, right? So this would be how the opposite of this algorithm would go. We'd say this is 0, and the controlling value would be 1, right? This would make this 0, and therefore we'd only have to do A is 0, and we don't care what B is, right? Because if we put a 0 on A, what's going to end up happening is we should get a 0 on the output of the AND gate, but what ends up happening is we'll get a 1, so we'll catch it. So the next part of the algorithm is, so we have 1 and 1 here. We're going to propagate this node F, and we're going to have D, because we're supposed to be 1 and we get 0. So we're going to be propagating D. So we're going to put D on the OR, and we need to, what we're going to do is we're going to be trying to push it to the output. So that means we're going to set this K value that was in our algorithm equal to H. H is this node, right? And that's going to make C equal to 1. And so what's going to happen is we have to figure out how to make this still be D, right? So in order to get D through, we have to have C is equal to 0. So C is equal to 0, that's going to put this here, and then D or 0 is going to put D here. Does that make sense? We have to somehow propagate this to the output. That's why we get I equals 1, therefore C equals 0. And so I don't care what D is. So let me get rid of this little version thing here, right? And so we're propagating H, D, X, or 0. Continue to come through here. Justify I. We got to get D to this output here, right? So what we're doing here is we got to figure out how do we propagate D through here. So that means I has to be 1, right? That's what that comes in, which means E has to be 0. So the specific input vector that we have to do in order for that to propagate the error to the output is 110x0. Does that make sense? And so we have properly found it. And so the reason why I presented this in different ways, I presented it in this way over here to show how it correlated to the algorithm, because some people learn better algorithmically. Some people learn better with examples, which is why I have included this over here on the right. So whichever one suits you best, whichever one makes more sense to you, that's the one you should work with.
Would you want to copy all of it down?
The one that you feel works better for you. These are the same. It's the same answer twice. I feel that would be redundant. Just as long as you somewhere you write down your steps and you include this, because you're going to have a test question involving what we're going to be covering next, which is the D algorithm. And what ends up happening is that I want to see your steps. If you go through your steps and you show me what you do, even if you get it wrong, you get the majority of the credit. So I want to see how you go through the algorithm, how you do this. So either way, you do it properly. So what we designed up here is what we actually, you see that's our result. We got the same thing. So the whole goal, we get a stuck at 0 fault. And with the algorithms, we got to get this fault to the output. So what ends up happening is we see stuck at 0. We use this justify with 0. That means we figure out using those equations that since it's an AND gate, we need a 1 and 1. We have to do all of them. I mean, the simple way to do this is I need 0 here. So in order, it would normally be 1. So I would need a 1, 1 on this input. 1, 0 is D. So now I need to propagate D to the next node here. Well, it's D, it's an OR gate. So I need to put a 0. I need a 0 here somehow, right? So that means G needs to be 0. That means I need one of my inputs for AND to also be 0. So that's 0 and don't care, right? Because you want to come up with the minimum number of inputs on your vector to make it work. Okay, so then we propagate D here. This portion of this propagate, what all that means common sense wise is that I need to get this output here somehow. Well, if I have D on the output, and I have a D on the input, it's 1, 0. So in order to have this work, I need a 1 on the output, because if it's 1, then it'll propagate D. If it's 0, it propagates 0, so it's going to be D. Does that make sense?
Can it also be where it's where the test is 1, 1, x 0, 1?
Yep. Because the algorithm states select one input, J. So to answer your question, as long as you select one of those two. So what George has asked is, is this a correct answer? Yes, it is. So what happens is, in order for that to work, we need 1 here, and then we get to 1, well, it's inverted, so that's where we get the 0.
Does it say anything about A and B, or is that understood where you want to set everything to 1?
Well, yeah, so that's in the algorithm, that's for each input. So in order to get a 1 on the output of an AND gate, you need to have all 1s. In order to put a 0 on the output of an OR gate, you need to have all 0s. If you put 1 on the input of an OR gate, you'll get a 1 on the output, which is this case, the select 1 input. So let's say you have a 4-input OR gate. You just do 1 XXX, X1, X, whatever one suits you best, as long as it's 1. Okay. Did I answer your question? So this is the correct answer here. And so the question becomes, well, what happens when you have fan out like this? So here we have some fan outs, right? So we have one propagates here. We have some issues here with this stuck at 1 fault. So when we perform the algorithm, we get the following inputs, right? We get 1, 1, 1, 1, X, right? But here's the issue. We end up a short version of this paragraph is what ends up happening is this loop, we end up getting a value 1, we get a 0 here, 0 here, we propagate the error, and here, here we're propagating E. So that way, no matter what, because of the fan out and the looping, we're not actually able to propagate the result using this basic algorithm. So but there is an algorithm that will solve this. Okay, so this is the one. Okay, the short version is what I've just said here is that it works better when you have a no fan out. So since percentage circuit it would be time consuming to use the algorithm about to present to find all the vectors. Use the algorithm in 9.10 for each stuck at fault. So if you look at the circuit and there's no fan out, do this. If you look at the circuit and there is fan out, do what I'm about to present next. Does that make sense? And then 8, I call it automatic test penetration, no fan out, circuit C. So the input, for those of you who've taken algorithms, you know you have to input the circuit notation. For each node in C, you want to generate the whole set of test vectors in order to be able to get this. So you could actually use this algorithm to generate an entire set of test vectors that will find every potential stuck at 0, potential stuck at 1 fault. So that means in many cases, you'll actually find that there's a minimum number of vectors that you need to use. You don't need to do, for example, this is a 4-input gate, and you don't need to do all 16 inputs to verify that it works. So if there's like 6 vectors that'll find all the stuck at 0 and stuck at 1 faults, you just run those 6 vectors, and if you get the outputs you're expecting, then you've tested all of all the gates, right? So when we talked earlier in this section about you do your formal verification, then you're doing your automatic test pattern generation, you have to test every AND gate. Well, it's not going through every single gate and checking the values, because that's also time consuming. Generating a minimum set of vectors to be able to find all of those things is what you need to do. And so what we're going to be using is we're going to be using this thing called the backtracking strategy in order to do this thing, this D algorithm that I've been alluding to. You want to search for a test vector, use this decision process. So what we're going to be doing is we're going to be making educated guesses to fill out these things known as the D frontier and the J frontier. So we're going to select alternatives for a line justification problem. So that means we're going to like try to justify a line and see if it works, and if it leads to an inconsistency, then backtracking. So the inconsistency means is that we believe we have a vector for a specific stuck at V fault, and then we propagate it, and there's some sort of fan out where we need to propagate it, but as a result, we're actually getting the opposite value. Then we need to backtrack and switch certain things. And when I go through the example, it'll make a lot more sense. And the whole goal is this recovery from incorrect decisions. And the whole point is it's supposed to address this issue that I showed up here. So what happens, we discover these don't work, and we backtrack and try something different. And so in order to do this, we have these concepts here. The D frontier are all gates whose output is currently undefined, but have one or more error signals on their inputs. So we have, let's say we have a 3-input AND gate, right? And so we have D on the input, but we have yet through the process of the algorithm put some sort of value on the output, right? So remember we were trying to propagate it to the output, and we would have D or 0 or 1 based on what we needed, right? So in this case, we haven't gotten there yet. So we're still on this D frontier. The J frontier is all gates whose output value is known but not implied by its input values. So for some reason, let's say we have some other gate where we figured everything out, 1 and 1, and there's some other value going out here. There's some fan in. Or it's an actual output, but we haven't gotten all the inputs yet. That's the J frontier. And when we go through the example, you'll see what the J frontiers and the D frontiers, and I'll explain those. A unique D drive, we're at the point where we're one gate remaining in the D frontier. So our whole goal is to get everything out of the D frontier and actually solve the algorithm and solve all of the nodes. So the 3-step implication process for the D algorithm. So you check all the values that can be uniquely determined by the implication. So let's say I have an AND gate input. I put 0 and that propagates 0, right? So we have some 0 and don't care. So what's going to happen is we need to determine how this affects everything else. If there's another AND gate over here, we propagate it forward. But let's say I don't need a 0 here. But let's say we've already figured out that there's a 1 here, or a D here, or a D bar here. We have to check for consistency. So eventually, if we get to the point where we have a 0, or let's say we have an OR gate and we imply that the output needs to be 0, but somehow we get a 1 here, then we have to backtrack because of our issues. And oftentimes because of fan in and fan out, these cause problems. And then maintaining the D frontier and J frontier, what that means is you basically are keeping a list of which nodes are still which gates are still in the J frontier, which ones are still in the D frontier. So this D algorithm, so I have this circuit, I have a set of nodes, I have a set of values, and so the specific node that I am looking for is stuck at, and the value is the specific value that it's stuck at. So if I have node F stuck at 0, then we have a circuit, all of the nodes, node F, 0. So while the primary output is X, so we determine the implications and set the values. So we're going to set the node value to V and try to see how that is implied. Checking the results, and then we're going to see if it fails, we have to backtrack and figure out how it failed and why. And then if the D frontier, then we are unable to find the error, and if J frontier is null, then we've succeeded. And the reason why is if the J frontier is empty, we have all the gates whose output is known but not implied by its input values. We've gotten rid of all of those. That means we know all the output values, we know all the specific input values. Therefore, we have properly gone through the circuit and determined, we've properly propagated the output, the error to the output, and properly determined the input vector necessary to do so. And so here's the example. Okay, so we have the same, we have a stuck at 1 fault on the input of this NAND gate here. So we want to use the D algorithm to determine the input test vector required to find this indicated fault. So step 1, we go stuck at 1 fault. That means we need to set A to 0, right? So if we set A to 0, what we need to do is figure out all the implications. So the implication means that this is 0. So we've put a 0 on the input of a NAND gate. Therefore, H must be 1, right? Therefore, we put a 1 here. That's one of our inputs. Using propagate, we know must be in B and C must be 1, right? So we normally you have a, if you have 1, 1, and 1, you're going to get a 0. And you're going to, but if you have a stuck at 0 fault, it should be 0, it is 1. So in this case, what's going to happen is it should be 0 and it is 1, right? I'm sorry, it should be, yeah, it should be 0, but it is 1. To use propagate, we know B and C, so therefore we propagate D to G, right? And so that third part, maintaining the D frontier and the J frontier. The D frontier, remember, it means we don't know the outputs, right? So we determined the outputs on G1, G0. We also have a 1 here, right? And we have a 1 here. So what that means is if 1 goes here, we put a 1 on the input of G3. We know that if it's a 1, it's going to be a 0. And if it's a 0, it's going to be a 1. So it's going to put E on the output. So E is going to go through here. Does that make sense? Likewise, when C comes through here, you're going to put a 1 here. So F, it gets inverted. So this is F bar, right? And then if F bar is 0, that means we're going to have a 1 here. And F bar is 1, we're going to get a 0, which means it just becomes an inverter. So again, we have F here, which is why G5 is on the J frontier, because we know the output, but we haven't uniquely determined the input yet. Does that make sense? That's what the definition of J frontier means. And then again, we have F, and then we have this D value, F and D. So if 1 and 0, if F is 1, that's going to be D1. If F is 0, it's going to be 0, so it's just going to be F. So that's why, I'm sorry, no, that's not right. Oh yeah, in G7, we have a 1 and E and well, G3 and G5. So we have E and F here. But here's the issue. So since H is equal to 1 and J equals 0, so what's going to happen is, let's say we put D is equal to 1. That means D bar is going to be equal to 0. So you got D here, right? That means this 0. This takes G1 out of the J frontier and makes I equal to D bar, because we're putting lowercase d versus uppercase D here. That means I is equal to D bar. Now we have taken G1 and G7 out of the J frontier. Since we have a 1 in D bar, that means we're going to have the opposite. So 1 and 0, when you don't have all inputs to a 1 on a NAND gate, it's going to be a 0 no matter what. I'm assuming it's going to be a 1 no matter what. Does that make sense so far? So step 3, since D bar is at I, so you put D bar here. The way to get the error to propagate to N is through the NAND gate, is to make all the other values 1. But we have a 0 there. Decision is J equals 1. So we got to make J If j is equal to 1, that means we need one of these inputs. So if we have E bar, and here we have 1 from the input, right? That means if you have a 1, 1, this would be a 0. So E bar has to be 0. That means E has to be 1. Does that make sense? So we're trying to propagate the result to the output, and we do that. But here's where the issue comes into play. So if E is equal to 1, then it's going to come here, right? So then we have D here. So this is right. E bar must equal to 0 for E. Since G is an input of G4, this makes K equal to D bar. Right? However, in order for this to work, we have K has to equal 1. So we said earlier that in order for that to propagate through, all the other values need to be 1. So therefore, we have a contradiction. So this can't be correct. So in order for that to propagate, we need to work. So therefore, since E equals 1, so if we make E equal to, since we had E equals to 1, since E equals 1 made the contradiction, let's start with E equals 1 and find the implications. So E equals 1, here's D bar. G3 is now removed, right? So we have 0 here and 1 here from D, right? 1 and 0 is going to put 1 there. So here's the thing, we need a 1 here, right? And therefore, what's going to happen is G3 is now removed from the J frontier, so we're getting closer. This means K is equal to D bar, right? So we're trying to propagate it this way. And this means J is going to be equal to 1. So now it works. K, yeah, okay, so this is where we hit our contradiction, right? So before, what ends up happening is we initially had K equal to, we initially had I equal to D bar, right? So we had the error here stuck at 0 here. So then we tried to figure it out. So we selected J is equal to 1. And so in order to do that, we already know B is 1. And we know C is 1, right? And we know A is 0. So we've come up with our 3 initial values. So in this case, what's going to happen is B is going to go here. So that means this value is going to be at 1. In order to get that value, this value needs to be 0, which means E needs to be 1. But what do we need to do next? Now we need to propagate it out. So it's now 1. And then this means we have D here. That's going to put D bar here. You see how this kind of fans out everywhere? What we need to do is we need to get all the values to be such that if you put D bar and D bar, if you NAND them, so if we had all 1s and then 2 D bar and D bar, it's the same thing as what happens if we NAND these two. So this becomes, right? So NAND becomes 0. 0 and 0 becomes 1. And 1 and 1 becomes 0. So it becomes D on the output. Since G is an input on G4, and it is D, then makes K equal to D bar. However, we've defined K as 1. So what this means is that we had gone through and gone, okay, this is D bar. We had 1, 1, 1, and 1, right? So what happens is we actually went through and said this was 1, this is 0, and therefore this is going to be 1, but we got D bar and the contradiction comes here. Does that make sense? So then what we do is we actually say, all right, so we're going to get rid of that and then figure out what it actually is. Since we have D here, we actually get D bar there. And same thing, we've said these are 1 and 1. So now we can, so that means we have K is now equal to D bar, which is what I've said here. E bar is equal to 0, and therefore E is equal to 0. And now we have J is equal to 1. So now this works up to this point. So we know that this node works, D bar works, 1, and D bar is correct. So now we have to see, are these values actually going to be 1? So if we have D here, right? So that's this input. We have C is 1, B is 1, and A is 0. So that's going to come here. So if we want a 1 here, we need to have, and we have a 1 here, we have to have a 0 here, right? So if a 0 here, that means F bar is 0, that means we have to have F is equal to 1. So then the next step becomes we actually test to see how F actually affects this. So this is 1 here, and we say we wanted a 1 there, but it's D, so it should be D bar. So that's where our contradiction is, so that's no longer correct. So then what we do is we actually say, well, the contradiction started at F equals 1, so we say F is equal to 1, so we put it here, and we get D here, so 1 NANDed with 1, 0, right? It's going to become 0, 1, which is going to become D bar. So now we have the nodes, and so when we have this set of inputs, we know what we can propagate. So here we have 1, all the ones in this case are, so we have 0, 1, 0, 1, and 0, 1. If the result of this is 0, then what's going to end up resulting is the output will be 1, and then if it's 1, then the output is going to be 0. So that means we're going to get D on the output, which means G7 comes out of the J frontier. Therefore, we've cleaned out the J frontier. The algorithm has worked, and we have propagated a result. So that means our inputs are going to be 0, 1, 1, 1, and I believe it was E was 1, right? Yeah, E, what is E1 or E must be 1. And then F was also 1. So that input combination, we will propagate an error to the output. Does that make sense? I mean, it's 10:15, lecture's over, so yeah, 0, 1, 1, 1, 1 is the right answer. So this is the simplified answer. I will start Wednesday's lecture by going over this example again. So on that note,